Hey everyone, today we have two lessons for you. Pretty fast, I think, hopefully, but we'll see. The first one is all about something called average rate of change. Calculus is a lot about how things change as time changes or as another variable change. How does the passing of time affect other things? And so in calculus, we study a lot about rate of change. And so today I'm going to refresh your mind on average rate of change. So let me start with a little intro for you. Let's say this is me and somebody, so this is like my intro example. Let's say I wanted to plot my time. So I'll use t. A lot of times I use t for time, and then I'll make this my distance, how far I traveled. Okay, so time 0, I'm starting at 0 distance. I've gone 0 feet so far. After 1 second, I've gone 2 feet. After 2 seconds, I've gone 4 feet. After 3 seconds, I've gone 6 feet. After 4 seconds, I've gone 8 feet. Okay. So this problem would be like an algebra 1 or integrated 1 problem. I could ask you something like, how fast am I traveling per second? So in this second, how fast did I go? From this second to this second, how fast was I going? From this second to this second, how fast was I going? And so on. And if you see, it's always a constant rate. I went 2 feet in that second. 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 So my speed, or my rate of change in this problem, was 2 feet per second. Always, based on those numbers, it looks like I was just traveling at a constant rate of 2 feet per second. And if I were to graph it, this would be otherwise known as the slope. So the slope is your rate of change. And this is a linear. If I graph this information, you would have a nice straight line that would tell you the distance traveled after each point in time. So at time 0, I was at position 0. At time 1, I was at position 2. At time 2, I was at position 4, or I'd gone 4 feet. At time 3, I'd gone 6 feet. So my slope, or rate of change, was 2 feet per second. Okay. So what if this was, so this is case 1. Pretty standard, integrated 1 level. But what if I gave you this case? We'll call this case 2. And I gave you another similar setup and a distance. And I asked you, okay, at time 0, 1, 2, 3, and 4. Time 0, I'm still starting out at 0 distance. Time 1, let's say I've gone 1 foot. Time 2, I'm at the position 4, or I've gone 4 total feet. Time 3, I've gone 9 total feet. Time 4, I've gone 16 total feet. Okay, well, what's my speed, or my rate of change this time? Well, if you try to do the same approach we just took, you notice something a little different. In this one, from time 0 to time 1, I went 1 foot per second. From time 1 to 4, though, I traveled 3. From time 4 to 9, I traveled 5. And from time 9 to 16, I traveled 7. So what's going on in this problem? Was I traveling with a constant rate of change? No, I was speeding up. I started going faster and faster and faster, as I tend to do. Because think about when you're starting up, you can run and then start really moving. At some point, you probably hit a top speed, but we only stopped looking after 4 seconds. So really, this doesn't make any sense. I can't ask you for the speed because it was always changing due to something called acceleration, which we're going to look a lot more at in this class. That's where this class starts to overlap with physics a little bit. Physics is all about acceleration and how it changes and things like that. So instead of saying my speed, I could ask you for something like this. What was my average speed, or average rate of change? What was the average I was going? Well, check this out. It looks like at the slowest, I was going somewhere around 1. I was probably going less, and then I sped up as I went. And then at my max, I was kind of going 7 or maybe even a little faster. So the average is probably somewhere in between these two values. somewhere around 3 or 4 or something like that. Maybe 4 or 5, depending on some things. So how do we find the average speed? Well, this is actually a pretty simple calculation. If you remember some things from integrated 1 when you first saw it, I think. All you have to do to find the average speed is just find the slope between the endpoints. Find the slope between endpoints. So if I were to ask you to find the average speed, I have to give you an interval. I have to tell you the average speed. I have to give you a function and a time interval. So we'll say over the closed interval, brackets, 0 to 4. So that means I want to know how fast was I running or traveling from time 0 to time 4 on average. So you take this as one of your points, and this is your other, and you just find the slope between them. Scroll down a little bit. You just find the slope. And the slope would be y2 minus y1 over x2. Oops. Oh, no, not an x. x2, which is 4, minus x1, which is 16 divided by 4, which is 4 feet per second. I traveled on average 4 feet per second. So an average is kind of like sometimes you were going slower, sometimes you were going faster. That's like an average. So it's like if you drive to work, maybe your average speed is 40, because sometimes you're on the freeway going 60, but sometimes you're driving through neighborhoods and going 25 or something like that. And so that's an average rate of change, or the average speed, and it's just the slope. So that gives us our formula that you're going to be using pretty much on the homework lots. It's to find the average rate of change. And I'm not going to keep saying average rate of change. I use something called AROC, which is average rate of change. To find the AROC over the interval a to b of a function f of x, here's your formula. The average rate of change is equal to f of b minus f of a. So what you get when you plug in b minus what you get when you plug in a over b minus a. And then you would just evaluate. It's just the slope that connects the endpoints. Okay, so let's do another example. And actually this time we'll actually do the same example, but we'll change things ever so slightly. So we'll say here's your function. This time let's do x squared plus 2. And I'll say something like find the AROC, or average rate of change, over, and I'll do the interval 2 to 4. It doesn't have to start at 0. I can do any interval I want. I could even have a negative interval if I wanted, like a negative coordinate. So from our formula right there, we see that the AROC should be f of 4. So what I get when I plug in 4 minus f of 2 all over 4 minus 2. Well, when I plug in 4, I get 16 plus 2, which is 18, minus, when I plug in 2, I get 6 all over 4 minus 2, which is 2. So 18 minus 6 is 12, and 12 divided by 2 is 6. 6 units per unit, depending on what. We didn't give this one a physics context, so we'll just say the rate of change is 6. 6. Okay, so what does that mean in a kind of graphing context? Because I want to be clear before we move on what we actually found. This part's pretty important. I'll probably ask you something about this. Explain this in your own words, because this is the importance of the average rate of change. If I were to look at this function, what I'm asking is, okay, notice from 2 to 4, this function's changing, right? It's increasing, it's going up, but it doesn't increase at the same rate. It gets steeper and steeper and steeper and steeper. So on average, how did this thing change? On average, And what you're telling me is on average, it changed at 6/1 units. It's almost like if I were to approximate this slope, it would be 6/1. But it's a bendy line. It's almost like you're saying, okay, but on average, the slope was about 6. The rate of change was about 6. So if I were to play something like, let me snip this and show you something. If I could go from this point at 2, 6 to this point, which is at 418. Of course, I ran out of room. And I could connect the dots. This line right here would have a slope of 6. Oops, sorry, I don't have the monitor up. So if I were to go from 2, 6 to 418, so 2, 6, 418, this line here, this blue line that connects the dots would have a slope of 6. And this blue line would show the AROC. And this blue line has a very special name called the secant line. So this blue line is called the secant line. A secant line shows the average rate of change. It has the slope matching the average rate of change. So the other thing I'm going to ask you to do in your homework is to find the secant line, or find the equation of the secant line. Okay, so what do I need to make a secant line? You need 2 things, a point and a slope. So you need a point. How am I going to get the point? Well, you already have the point. I gave you 2 x values. Think of this as x1 and this is x2. So typically what you're going to do is take x1, so your x coordinate, which is your a, and then the y coordinate associated with it, so f of a. You could choose the other one if you wanted. So listen, you could choose 4 if you wanted also. It doesn't make a difference. You need to use one or the other. And then you need a slope. And the slope is just the AROC, average rate of change. All right, and then you put them together using what I like to use is called point slope formula. So point slope formula looks like this. Y minus. This is where your y coordinate goes, which was f of 2, because we're using 2, and f of 2 was 6. So y minus 6 equals, this is where your slope is going to go, which is also 6, times x minus, and then this is your x coordinate, which is 2. And that's it. You can stop there. You don't even have to simplify. That's the line. And here's why I don't care if you simplify or not. Remember what I told you, the secant line should connect the dots for you. Let's see how I did. Y minus 6 equals 6 times x minus 2. And did it work? Check it out. Connect the dots, and we'll see it even better on the next one perfectly. And that blue line is called the secant line, showing me the average rate of change. Now, if you notice, I was very lazy about simplifying. Yes, you could distribute the 6 and then add 6. Well, you don't need to do that. This is fine. I kind of like this better. This is called point slope formula. Point slope formula. Okay. So at 13 minutes in, that's what you're doing on the homework. I'm going to do another example, but I'm not going to say anything else new. That's the gist of it. If you feel like you got it, I would go on to the homework. If you feel like you got to see one more example to kind of get the idea, I will show you one more example with a different function and a different interval. So let's say I gave you this function. Find the AROC, or average rate of change, of this function, g of x, equals, let's do radical x minus 3 over the closed interval, so from the actual point to the actual point, of 7 to 12. Then find the secant line. So then find the equation of the secant line. Okay, this is a pretty typical problem. We're going to have a function, we're going to have an interval, we got to find an average rate of change. So sometimes it's helpful to identify everything. This is your a value, this is your b value. This is not a coordinate, this is an interval. They are not both x and y, they are x1 and x2. These are x coordinates, okay? Do not treat this as a coordinate. I see it every year with a couple people thinking that this is, I should make that clear, x. These are x coordinates, okay? All right, so the AROC, to find it, would equal f of b minus f of a, those are your y's, over b minus a, otherwise known as the change in y over the change in x. Okay, so let's evaluate. When we plug b in, we get square root of 9, which is 3. Minus, when we plug 7 in, we get 7 minus 3, which is 4. Square root of 4 is 2. All over 12 minus 7, for a final average rate of change of 1/5. So that number kind of tells you that this function is really not changing very much from 7 to 12. And when we graph it and look at it, we'll see that this is really not changing. Radical functions start steep and then they grow very slowly, very slowly. There's only one function that grows slower, and we'll talk more about those later. But let's make the secant line. So that's just half the battle. We still got to find, bring it over there. Let's make that secant line because we can visualize how the average rate of change looks for this function. So the secant line is y minus your y coordinate, which was, I'm going to use this one this time and this one. So this time I'm actually going to use the coordinate b f of b, just to show you that you could use either one. So the coordinate I'm using is b. Make sure you plug f of b in here. This is 3. This is what you get when I plug the 12 in, equals your slope, which is the average rate of change, times x minus 12. And that's good enough. We could simplify, but like I said, I don't need you to simplify right now because Desmos can deal with this. If we were in my class, we'd have to get y by itself, so we could use our graphing calculator. And then, as always, check on Desmos. You get a free pass to make sure you did everything correctly, so take advantage of it. So let's see. We have our function, square root of x minus 3. Where is it? There it is. And remember, we were trying to find the average rate of change from 7, which was here, to 12, which is here. So what I want to see is a nice line connecting the dots from 7 to 12. A nice linear straight line connecting the dots. If I did everything correctly, that's exactly what I'm about to get. 5 minus 3 equals 1/5 is 0.2 times x minus 12. How did we do? Well, it's practically on top of it, but you can see that, yeah, it goes through 7.2, they both do, all the way up to 12.3. Nice average rate of change. It shows how this changed on average. Sometimes it was steeper, sometimes it was shallower, but on average it changed at 1/5 units. The change in x was 1 over the change in y, which was 5. Sorry, I had that backwards. The change in y was 1 over the change in x, which is 5. Okay, so that's one. Go ahead and practice these on the homework. Average rate of change is going to pop up all year. It's a pretty simple calculation, but definitely something we're going to need, okay? So the gist of it is all right there in those two examples I did for you. All right, and we'll stop there.